This presentation introduces the capability curve and discusses target CPK and shows how to use Tolcap to find the tolerance required to achieve a target CPK. You watched the earlier presentation about getting started, but you're not sure you understand it all? While our introduction describes the recommended way to use Tolcap, some users find it daunting. Okay, you know the dimension and tolerance, you can choose a process and material, but the geometry and additional variation questions are too hard. These slides go through a simplified approach. It doesn't have the precision of the full analysis, but it puts some reasonable brackets around the process capability estimate. Let's go back to the example in our introduction. We're machining, turning and boring a dimension of 100 plus or minus 0.035 in a part made of mild steel. Last time you selected the turning and boring map in the machining section and entered the dimension and tolerance of interest 100, 0.035 and clicked calculate. Then you clicked on the MP Wizard button and selected mild steel to get a predicted CPK of 1.95. Now, instead of opening the GP Wizard, click Show Curve in the Using Tolcap panel. Look at the yellow dotted line rising vertically from 0.035 on the tolerance axis. It meets the blue best case curve at CPK equals 1.95. But in the worst case, geometry and additional variation might lead to the result on the red line, little better than CPK equals 0.5. The script below the curve suggests that to achieve CPK equals 1.33 would not be possible with a tolerance reduced below 0.22 millimeters, and might need to be increased to 0.63 millimeters, because that's where the red worst case line crosses CPK equals 1.33. In fact, in our example, GP and VP analysis reduced the CPK estimate to 0.97, and we can show that a tolerance of plus or minus 0.045 would suffice to achieve CPK equals 1.33. It's best to do the analysis, but the capability curve will give you safe, though conservative, limits. You may well have noticed that Tolcap defaults to a target CPK of 1.33. Why? Well, the Tolcap database is well established and it predates the Design for Six Sigma bandwagon. The requirements of good practice at the time were similar. Essentially, it was still necessary to design for Six Sigma because the first off-tool parts had to demonstrate CPK equals 1.67, which is 5 sigma, and a margin for error is needed. Series production parts had to maintain CPK equals 1.33, which is 4 sigma, all the time, and the Tolcap database was tuned to estimate ongoing CPK with that target in mind. While CPK equals 1.33 allows 33 parts per million out of tolerance, rather than 3.4 parts per million if CPK equals 1.5, experience has shown it works. But then again, I suppose design for 5.5 sigma wouldn't sound as good. That said, it's your choice. If you want to design to CPK equals 1.5 or any other value, change the CPK threshold value on the capability curve. Rather than finding what CPK is likely to result, if you set a certain tolerance, you can use Tolcap to find the tolerance required to achieve a target CPK. Click the CPK tab and then enter the required target CPK. Watch the tolerance change as you select the map and run the wizards. We hope these introductory presentations have shown you why Tolcap is a unique and vital tool for designers. Setting achievable tolerances saves your organisation significant costs and saves you a lot of that stress and distraction sorting out designs that could otherwise turn out not capable. Tolcap helps you to check the capability of a tolerance or generate a tolerance with a target capability. Our next presentation will explore the problems with tolerance stacks and how Tolcap provides solutions essential for statistical tolerancing. Thank you for listening. For more information, please visit www.tolcap.com.